Hello everyone, and welcome to Physics Society and to the third talk this Michaelmas term. My name is Gia and I'm the president. We're joined today by Yikwon, who's our publicity officer, Rob, who's our IT officer, and Ada, who's our academic officer. Thank you for coming all, and we're delighted to introduce you to our speaker, Rahil, for his talk on chaotic adventures of active particles.
Thanks. Thank you. Thank you for having me, and thank you all for being here on a Thursday evening. So what I'll do today is I'll talk about active particles and specifically their chaotic dynamics that arise when you are trying to understand motion of active particles. So just to get an idea, how many of you have heard of active particles or active matter before? Just if you could do a show of hands. 1, 2, okay, perfect. Right, so what I'll do is I'll probably start by giving you a very brief introduction to what are active particles and what is active matter. So we'll start with that. And then we will go over some ideas, some concepts from nonlinear dynamics and chaos. Some of you might already be familiar with it, so just so that everyone is on the same page, we'll just review some of those. And then what we'll do is we'll try to see how some of these ideas from nonlinear dynamics allow us to rationalize some of the complex dynamical behaviors that arise in these active particles, right? So we'll look at two examples. So the first example we'll look at is an active particle in a fluid flow. So that's the first example. And the second one, I'm going to talk about superwalking droplets, and then I also have the actual experimental setup here. So after the talk, you can play around with the droplets yourselves. All right, so before I tell you what is an active particle or what's active matter, let me tell you a bit about the evolution of this field. So here is a snippet from a recent paper, which is a meta-review. So it's a review paper that contains references to all other review papers in active matter, right? So you can kind of see by this that it's like a growing field. And one of the plots in this paper is this, where they plot the number of review papers every year that have the word active matter in it, right? So it's not the number of papers, it's the number of review papers. So each of those review papers will themselves have citations to many of the actual research papers on active matter. So you can kind of notice two things from here, right? That it's a relatively recent field, right? So it really took off like 20 years ago or so, and you can see it's growing quite rapidly. So even though it's growing quite rapidly and it's very interdisciplinary, you also have papers which have titles like this. So what exactly is active matter, right? So because more and more systems are now coming under this umbrella of active matter, researchers in the field, they are trying to iron out the details on what systems to classify as active systems and what not to, right? So what I'm going to start with is I'm going to give you a working definition of an active particle that is used by many researchers. But as you see from the title of this paper, there is no completely agreed upon definition as such. All right, so for our purposes today, an active particle is an entity that consumes energy and it converts it into some sort of mechanical work, usually persistent motion, right? So in doing this conversion, it also dissipates some energy. So therefore, these active particles, they are not in thermodynamic equilibrium, right? So they are non-equilibrium entities, right? So to give you some examples, active particles, they come in all shapes and sizes, and right from the nanometer scale all the way to meters. And they include both living organisms or synthetic systems as well. So right at the nanoscale and the microscale, if you think about biomolecules within a cell, right? So molecular motors such as kinesin, myosin, and so on, all of these are active particles, and they perform various processes within a cell, right? So you have something right down at the nanoscale and microscale, and then a biological cell itself is an active particle. And then as you keep going up the scale, you have bacteria, for example. So here is a video of a white blood cell chasing a bacterium, right? So the white blood cell, it eats food and gets nutrients from its surroundings, and then it's using that energy and converting it into this crawling motion, right? So it's an active particle there. Here you see an E. coli bacteria. So these are microorganisms that are immersed in a fluid medium, very viscous. And here the E. coli is using its tail to propel itself. And you can see that it moves persistently in one direction, and then it reorients. So it's doing what is called a run and tumble motion, right? So you have an active particle, a bacteria there, which is doing this run and tumble motion. Here is a synthetic system of an active particle, which we are going to look at in detail today. But it's a droplet which is bouncing and walking on a vibrating bath of the same liquid, right? So it's an active system, but it's not a living system. And then another example are robots, right? So they can do persistent motion, either pre-programmed or by sensing environment. And there they are mainly converting electrical energy into mechanical motion, right? So you have these various examples of active particles going right from the nanometer scale all the way to micrometers and millimeters. And then on the meter scale, you have birds, animals, fish, even we are active particles, right? We eat our food and use it to do various sorts of mechanical motion throughout the day, right? So that kind of gives you an indication of what is an active particle. All right, so now let's move to active matter, right? So active matter is matter which is composed of a large number of these active particles, right? So usually in your usual phases of matter, solids, liquids, and gas, the constituents are atoms, right? So in the same way, in active matter, the constituents are these active particles. And as I told you on the previous slide, these are non-equilibrium entities, right? So these individual particles, they are out of equilibrium. So the collective phases they form, they are also out of equilibrium, right? So let's have a look at some of these emergent behaviors that arise when you have a lot of these active particles interacting with each other. Right, so the first one here, which kind of got this whole field started back in the 90s, is flocking and murmuration of birds, right? So you might have observed this yourself, but when you have a large number of starlings, they perform this very coordinated collective motion, and you get these emergent dynamic pattern forming, right? So there have been models developed in this area of active matter that try to explain and understand these collective flocking behaviors. Now, not only birds, this flocking type behaviors, they can also arise at the level of cells. So what you see there is our epithelial cells. So think of this as cells that form your skin, for example. So such cells, they can do this coordinated motion. For example, let's say if you cut your skin and the skin is trying to heal itself, then cells will perform this coordinated flocking motion to heal the skin, right? So you have this collective behavior going on at the level of cells as well. Here is another example of from a simulation. So what you are seeing here are a bunch of active particles that are interacting with each other, but the interaction between them is purely repulsive, right? So the interaction is purely repulsive, and yet you see these clusters forming, right? So what's going on here? So because these are active, they don't usually follow the conservation of momentum and conservation of energy, right? They are out of equilibrium. So what that means is that if you have two active particles which are coming towards each other, they won't undergo elastic collision. They can hang around each other for a while until one of them decides to move away. So what happens is that if two active particles come near each other, they will slow down. And you get a positive feedback loop where if they slow down, you accumulate more active particles. And if you accumulate more active particles, the new ones coming in will slow down. So this positive feedback loop gives rise to these clustering behaviors, even though the interactions are purely repulsive, right? So it's called motility-induced phase separation because the clustering is due to the motility of these active particles. And then the last example there is turbulence, but it's turbulence at the micro scale, right? So what you are seeing there is the coordinated motion of lots of bacteria, right? So when you have lots of bacteria, they can do this spatiotemporal chaotic motion, which is called active turbulence. Now, this is again different turbulence from the turbulence that you see in the atmosphere, right? And the big difference is the scales. So this is happening at the micro scale. So your Reynolds number, which is a number that characterizes the inertial forces to the viscous forces in the fluid, it's very small. So these bacteria, they are swimming in like honey, essentially, right? So the flow itself is by itself is nice and smooth, but these bacteria, due to their activity, they stir up the flow and make it turbulent, right? Whereas, for example, when you have turbulence in the atmosphere, it's coming from the inertia of the fluid itself, right? So you can see all of these interesting collective behaviors when you have these active constituents in large numbers interacting with each other in different ways. All right, so let's move from active matter to nonlinear dynamics, and then we'll try to bridge the two. So as physicists and also applied mathematician, we try to make sense of like various physical effects that are going in the world by coming up with mathematical models, right? And much of the artistry of this process lies in identifying the relevant variables of interest to the phenomena that you are studying, and then writing down the equations that kind of govern the evolution of these variables that you are interested in, right? So many times when you try to write down these equations, they take the form of differential equations, right? So let's say if we have some variables of interest, x1 to xn, right? Then many times when we try to write down mathematical models, we will come up with a dynamical system, right? So a system that describes the evolution of these variables. And in a sense, the functions or what describes the evolution does not always have to be linear. It can be a nonlinear function, right? So if I have some set of variables x1 to xn, and I write it in a vector form, right? Then I get a dynamical system, and this function on the right-hand side, it can, in general, be a nonlinear function, right? So when you have a dynamical system like this, it's useful to abstract out and go into a space which may not be a physical space, but an abstract space made up of all these variables, right? So this is usually called the phase space of the dynamical system. Right, so in this phase space, each axis is one of your variables. So any point on this phase space describes the state of the system, right? The complete state of the system, if you have accounted for all the variables. And as the system evolves, you are essentially traversing a trajectory in this phase space, right? So it's useful to go from what the variables are describing physically to this abstract phase space and try to understand what's happening in this phase space, right? And you can get different kinds of behaviors in this phase space depending on the nature of your dynamical system. So now there are many ways you can classify these dynamical systems, but for our purposes today, we are going to classify them based on whether they are conservative dynamical systems or dissipative dynamical systems. So let me start with conservative dynamical systems. So in this phase space, if you take a volume, right, a square or a cube, then you evolve the system. If the volume of this cube stays constant over time, it's a conservative dynamical system, right? The volume can get distorted and stretched and so on, but the volume itself will stay conserved, right? And a classical example is your pendulum, right? So in a pendulum, you can describe the motion of the pendulum by two dynamical variables, right? The orientation, theta, and the angular velocity, theta dot, right? And the phase space formed is a two-dimensional phase space in this case. And then when you have this back and forth oscillatory motion of your pendulum, you are traversing a closed loop in this phase space, right? So that's one example. Now, if the phase space of a conservative system is high dimensional, so if it has more than 2 dimensions, then there is a potential of more complex behaviors arising, right? So for example, you might have heard of the double pendulum or the 3-body problem. And if we look at the double pendulum, now the number of variables you need to describe this system are 4, right? The angular coordinate of each and the angular velocity of each pendulum, right? So the phase space is 4-dimensional. But it's not really 4-dimensional because you have things like energy conservation, for example. Then that gives you extra constraints in your system, right? So with that energy conservation, you have a 3-dimensional phase space. Now, what you're seeing here are 2-dimensional projections of each of those 4 coordinates. And you can see that as the system evolves, the patch, it starts extending, folding, and doing this crazy thing, right? However, the volume will still stay constant, right? Because it's a conservative dynamical system, but it gets distorted and convoluted in complicated ways, right? And you can see that it's doing this chaotic motion here, right? Because if you start the pendulum with almost similar initial condition, after some time, you can see that their motion becomes completely uncorrelated with each other, right? So you can have chaos in conservative dynamical system, if your number of variables are large enough. And this is a well understood thing. There is a whole field called conservative chaos, right? Which kind of studies chaos in these conservative dynamical systems. All right, now let's move to dissipative systems. So in dissipative systems, the phase space volume will shrink with time, right? And hence they are called dissipative systems. So if we go back to our pendulum, if you have friction, right, then if you look at your pendulum and again plot the phase space, then you can see that it will do back and forth motion, but eventually the back and forth oscillations will die down and it will come to a stop, right? So you have the volume of the phase space shrinking with time there. Now, dissipative does not always mean that everything will just come to a stop. Again, if you have enough dimensions, then you can also get oscillatory motion in dissipative systems, and you can also get chaotic motion in dissipative systems. So one very famous example is the Lorentz system, right? The Lorentz chaotic system, which was discovered in the context of atmospheric turbulence. So we are going to again revisit this Lorentz system in one of the examples again today. But you can see that you can have conservative systems or dissipative systems, and they can both display simple as well as complex motions, depending on how many variables there are and the nature of the nonlinearity of the dynamical system. All right, so having introduced these concepts, let's move on to our first example. So what we are going to do is we are going to consider very minimal theoretical models of an active particle here flowing in fluid flow along a channel, right? So the kind of active particle that you can have in mind here is a microswimmer, right? So something like a bacteria, a cell, or a microrobot that is designed for targeted drug delivery applications, for example, right? So a microswimmer, which is an active particle which is moving in a fluid medium, it commonly experiences confined environments, right? So think of pathogens moving through blood vessels in arteries and so on, right? So you can have this confined channel-like environment through which these microswimmers are trying to move. And in a common situation like that, you can have unidirectional fluid flows. So there you will have flow of the fluid in which they are immersed, but they will be unidirectional because you're confined mainly along the other directions, right? So here is the setup of the system that we are going to consider, right? So we have a confined channel, 3-dimensional channel, and we have a fluid flow going along the z direction, right? The fluid flow is unidirectional, but it's not uniform, right? Because the fluid at the walls the fluid can't move that. It has to satisfy a no-slip boundary condition because it can't drag the wall with it, right? So because of that, you get a fluid flow which is parabolic here. So the fluid flow is maximum at the center of the channel, and then it kind of decays down as you go towards the edge of the channel. So the fluid flow is unidirectional, but it's not uniform. It will change, the magnitude will change as you move around in the cross-section. And we are going to consider a simple point-like active particle in this fluid flow. So here are a couple of equations that describe this active particle interacting with this fluid flow. So let me tell you what are the assumptions we are making. So we are saying that the active particle is very small compared to the channel. So it itself does not disturb the background fluid flow, which is from left to right, unidirectional. And we are not going to consider any interactions of the active particle directly with the wall, right? So the particle only feels the flow and gradients in the flow, okay? So here are the two equations that describe the motion of the active particle. So our active particle, it's a very simple active particle. All it wants to do is it wants to move at a constant speed v0 in some given direction e hat, right? So that's all it wants to do. So if there was no fluid flow, it will just move at a constant speed persistently, right? So that's the active particle. Now, because we are in the microscale, which is the low Reynolds number regime, the equations of fluid flow, they are linear partial differential equations. So in a sense, what that means is you can superimpose solution, right? Because they are linear equations. So what we are saying here is that the velocity of the active particle is its intrinsic velocity, which it wants to move at, which is this v0, plus the velocity it gets advected due to this background flow that's flowing over, right? So this background flow is unidirectional, and then on top of that, you have this intrinsic active velocity, right? And we superimpose those, and that gives the total velocity of the active particle. Now, the orientation of the active particle, it will change with time as well. And the reason that will change is because my fluid flow is not uniform. So different layers are moving at different speeds. So if you imagine putting a circle in there, the top layer is moving faster than the bottom layer. So this will exert a net torque on the circle, right? So because of that, you will have rotation of the orientation of the active particle. And that's what this second equation is describing, that the orientation of the particle will rotate, and it will rotate based on the gradient of this flow. So it's called the vorticity of the fluid flow, right? So my active particle wants to move persistently, but it can't. Flow will keep on rotating it, so it will do some interesting motion because of that, right? So that's our simple theoretical model. Now, in this paper, where they first analyzed this model, they started with a simple 2D situation. So we are not going to go even 3D. Let's start with 2D first, right? So I have fluid flow from left to right, but my particle can only move in one dimension transverse to that, right? So we have a two-dimensional fluid flow. So if we were to look at those equations and translate them to these two dimensions, then this is what they become. So here, x is the direction along the width of the channel, right? So we get x dot is minus sine psi, which is saying basically the active particle velocity in the x direction is the projection of its velocity in that direction, right? So the projection of the angle. And then the second equation is that rotation part that I was describing before. Now these equations, they look a bit different from before, is because we have non-dimensionalized the fluid flow based on the active particle speed, right? So active particle speed is 1, and it's absorbed in this variable Vf. So you get these two equations, but if you eliminate x now from these equations, you end up with an equation for just the orientation angle, and that looks like an equation of a pendulum, right? So we can understand the motion of this active particle interacting with this fluid flow just by looking at what a pendulum does. So if you go back to first year physics now, we have a pendulum right? It can do two types of things qualitatively, right? It can do this back and forth motion about an equilibrium point. Now, what that corresponds to in the active particles case is, I have a flow coming in this direction. My active particle will point against the flow, and it will do this small amplitude oscillations while pointing against the flow, right? So that's what corresponds to this back and forth motion of the pendulum. Now, the pendulum, if you give it large enough initial velocity, it can also do the rotation motion, right? It can do a full 360. And again, in the active particle case, what that corresponds to is that away from the center of the channel, where the shear rate or the flow gradient is high, it will again point there, but it will do a full 360 motion and tumble, right? So you get swinging motion and tumbling motion of these bacteria, and essentially you can map them onto the equation of a pendulum, right? And this is not only theoretical. People have done experiments by confining some of these bacteria in these microchannels, and they do see these upstream swinging motion and so on, and tumbling motion. Right, so it's a very simple model, but it captures the essence of the behavior, that you get these two distinct classes of motion. Now, in this paper, they also extended it to 3D channels, but keeping the cross-section circular. And in that case, you get extensions of these swinging and tumbling motion to 3 dimensions. Now, what we are going to do is, we are going to consider a very general situation. We are not going to consider a specific cross-section to start with. We are going to consider a general situation. So these were the equations that I wrote down at the beginning. Now, if we convert these equations into Cartesian coordinates, components form, then we end up with these 6 equations, right? So the first equation for the position, you get 3 equations, x dot, y dot, and z dot. And the equation for the orientation, again, in the Cartesian components, you get these 3 equations. Now, these look horrible, right? Now, if you look at the z equation, you don't care about the z equation here, because the z variable does not couple into any of the other equations. So the z equations you can ignore for the time being, and you can integrate that separately. So essentially, you have now 5 equations that you need to deal with. However, we know that the unit vector, the unit vector has unit magnitude, right? We know that ex squared plus ey squared plus ez squared is 1, right? So we don't have to use 3 variables, ex, ey, and ez. We can reparameterize the unit vector in terms of angles, right? So this is the surface of a sphere, right? So you can parameterize the surface of a sphere in terms of angles, and you end up with 4 equations now. Right, so the new things you have here are 2 angles. So you have an angle phi that tells you whether you are pointing against the flow or towards the flow. So when phi is 0, you are pointing against the flow. And when phi is pi or minus pi, you are pointing in the same direction as the flow. Now, there is also another angle, because we are in 3 dimensions, which tells the angle in the direction transverse to the channel, right? So this is the angle in the cross-section. Now, this dynamical system, if you do the math, it turns out it's a conservative dynamical system, right? So just keep that in mind, right? Based on what we were discussing a few slides earlier. All right, so you can solve those equations numerically using your favorite numerical solver. This is what you get out. So I'm going to show you 2 simulations. The only difference between the 2 simulations is the starting point I choose for the particle. So in this first simulation, I've chosen the particle to start near the center of the channel. And if it starts near the center of the channel, this is what it does. So the panel on the left is the view along the channel. The middle panel is the cross-sectional view, and the plot on the right is showing the orientation of the particle, right? So you can see that it's pointing against the flow. So the flow is from left to right. So it's pointing against the flow, and it's doing this swinging motion, right, that we would expect it to do, right? Now, if it does not start near the center of the channel, if it starts away from the center of the channel, then first of all, you can see it's doing this full 360 tumbling motion. but it's not doing anything regular like it did in the other case, right? It seems to be doing this kind of random motion, taking turns and changing orientations every now and then, right? So it's doing this very, very complex motion, and definitely not something like a pendulum, right? So it's doing quite complex motion here. So to get a full appreciation of the different kinds of behavior that you get, here is a plot showing the qualitatively different types of trajectories that you can get in the system based on where you start. So the top plot, this colored plot, the x-axis is my initial starting location in the x direction, and the y-axis is my initial starting location in the y direction. And the color is what type of motion I get based on this. So let's try to understand this. So if you start near the center of the channel, you either get green, light blue, or dark blue, right? And all of these, as you see in the trajectories, they correspond to this swinging motion that we have been talking about. So if you start near the center of the channel, you do this nice regular motion that the active particle did in the 2D case as well. Now, if you start in these red regions or these purple regions, that's when you start seeing these more complex chaotic motion, right? So that's happening away from the center of the channel. However, it's not always true. You have these special yellow regions where it seems to be doing something nice and periodic motion and quite confined, right? So it's doing a large diversity of motion, and all of this is just based on where it starts. I'm not changing the parameters in the system. It's fixed based on the initial condition. It can do these different things. Now, the bottom plot you see here, it's plotting what's called the largest Lyapunov exponent. So it's a measure of whether your system is regular or chaotic. And the way you do that is you start with two initial conditions nearby, and you see that if the separation between the trajectories, if it's increasing or decreasing, and if it's increasing and increasing exponentially, you measure the exponent, right? So wherever you see purple region here, the largest Lyapunov exponent is either 0 or negative, which means regular motion. And wherever you see orange or yellow region, that's where you have chaos in the system. Right, so you can see that you have this complete mess of all the different kinds of motion. How do we make sense of this, right? We need to make sense of this. All right, so let's go back to our equations that we wrote down, right? We wrote down these 6 equations. We said Z wasn't relevant, and we had constants of motion. So one is that the orientation vector is a unit vector. Now, it turns out you get another constant of motion in the system, which is this quantity, right? So it's related to the fluid flow and the Z component of the particle's orientation. So what I mean by a constant of motion here is that if you look at this quantity, as the system evolves, this quantity is not going to change. It's going to stay fixed with time, right? So we have a 5-dimensional system because we have 5 equations, but we have 2 constants of motion. So effectively, it's a 3-dimensional dynamical system, right? Now, it turns out, and yeah, we said before it's a conservative dynamical system. Now, it turns out that we can map this system onto a Hamiltonian system, right? So if you have done Hamiltonian systems in classical physics, then you might recognize these equations, right? So these are your Hamilton's equation, right? So you have coordinates and momenta. So we can map this system onto a Hamiltonian system, and this is how the mapping plays out. So when you write down the Hamiltonian for the system, the momenta of the Hamiltonian, they correspond to the velocity of the active particle within the cross-section. So within the cross-section, I have 2 components of the velocity, right, in the x and the y. And those 2 components, they map to the momenta of the active particle. Now, what maps to the potential energy? So this thing maps to the potential energy. So the potential energy depends on my flow field, u, what is the shape of my background flow, but it also depends on this c here. Now, what is this c? So this c is a constant of motion, so it's set by the initial condition of the system. So how I start the system sets this C value, and this C value then tells me what is the shape of my potential landscape, essentially. So what's happening is the motion of the particle is being set by its initial condition, because the initial conditions determine what is the potential landscape available for the particle to explore. So if my particle starts near the center of the channel, then this is how my potential landscape looks like. So I'm only restricted to move within this region, and that's why the motion that we get when the particle starts near the center is this swinging motion, which is confined near the center of the channel. But if you start away from the center of the channel, then the landscape looks like this ring structure. So that's why when you start away from the center, you get these trajectories which are confined away from the center and never visit the center, right? So we can try to rationalize these complex behaviors and the way they get confined in the channel in terms of a Hamiltonian system where the potential energy depends on how my flow field looks like and also my initial conditions, right? So this is one way you can map this complex system onto a Hamiltonian and try to get a sense of the behaviors in the system. All right, so let's move on to the second example of superwalking droplets. All right, so I have the system here, but you can play with it at the end. But essentially, the idea is that if you take a container filled with liquid and you oscillate it vertically, then above a critical amplitude of oscillation, the free surface of the liquid, it will become unstable, and you get these standing waves, which are called Faraday waves, because they were discovered by Michael Faraday back in 1830s, right? So you take a container filled with liquid and you shake it. Below a certain threshold, nothing happens, and above this threshold, you get these Faraday waves. Now, if we are just below this threshold, so the surface is flat, so we are just below this threshold, and we create a droplet of this same liquid, then this is what happens, right? So back in 2005, Yves Scudder and colleagues in Paris, they discovered this. They saw that if you take a droplet of silicon oil and you place it on a vertically vibrating bath of the same oil, then the droplet can bounce on the liquid bath forever. And not only it bounces, it can start walking horizontally as it bounces on the liquid bath. So what's going on here? So each time the droplet bounces, it excites a little wave around itself, right? So each time it bounces, it excites a little wave around itself. Now the wave it excites, these are standing waves, so they just oscillate up and down, but they decay with time. But the time it takes for them to decay is quite long. So when the droplet comes back on the second bounce, it still feels the wave under it. And the slope, the gradient of this wave, drives the droplet in the horizontal direction, right? So you can get droplets that are walking horizontally on a vertically vibrated liquid surface. Now, three things to note about this system. First, the system is active, right? As in our definition of what we call active particle. And this is because even though the entire container is vibrating, the droplet extracts the energy locally, and it's converting that into this persistent walking motion, right? So it is an active particle. Second, the droplet and its underlying wave, they are coupled completely. So if I were to poke the droplet, then the underlying waves would decay and the surface would become flat. So the droplet excites the wave, and the wave, through its gradient, is guiding where the droplet goes, right? So the droplet, the particle, and its wave, it's a single entity. They are composed together, right? So the wave and the particle go together here. And the third thing, the system has memory, right? And this is because the waves that the droplet creates, they decay very slowly in time. So the droplet is not only affected by its most recent wave, but also by the waves it created, let's say, 20 bounces before. because it hasn't completely decayed yet, right? So you have memory in the system as well, right? So these are the three key features, right? And that's why I like to call these active wave particle entities, right? Okay, so let's look at a simple model of this system, and let's try to write down an equation of motion for these droplets. So the video you see here, it's the same video from before, but it's strobed at the bouncing frequency. So you only take one image of the droplet per bounce and stitch those images together. And because you're only taking one image per bounce, you don't see the bouncing motion, you only see the horizontal walking motion, right? And a widely used model for these droplets, which is called the stroboscopic model, it essentially does the same thing. You average over the fast bouncing time scale of the system, and you write down an equation for the slow walking motion that you get in the system. So this is what the equation of motion looks like for the particle. So we are going to do some simplifying assumptions so we can write down a sensible equation. So we'll say that the particle can only move horizontally in one dimension, right? So we only have one dimension x. And the equation you see there, it's essentially your F equals ma, right? So, but in dimensionless form. So the first term there is your inertia. So you can think of your kappa as a dimensionless mass. So you have inertia in the system. There is dissipation in the system. So when the droplet goes in air, there are drag forces it experiences. And whenever it impacts the liquid, it dissipates some energy as well. So there is dissipation in the system, which is modeled proportional to velocity. And the horrible looking integral term on the right-hand side is the kick that the droplet gets from the underlying wave. So let's try to unpack that one by one. So first of all, why is there an integral there? Because at each time, the droplet creates waves, but they decay very slowly. So I have to take into account all the waves droplet created along its entire history to determine its motion, right? And it's not a sum, and it's an integral and not a sum, because we have averaged over the bouncing, so there is no bouncing in the model. The droplet is continuously moving. So at each instant, it's creating these waves, right? So that's why we have an integral. Now, what is this f function? So this f function is the gradient, the slope, of the waves that the droplet generates. So if we say that the droplet generates some shape a of x, then this f is the gradient of it, right? Because what the droplet feels when it moves horizontally is the gradient of the waves, right? And this exponential term is saying that each wave that the droplet creates, it dies down exponentially with time, right? So a droplet creates waves, and it's building up these overall wave field, but these past waves, they are exponentially damped, they are dying down with time, right? So I calculate the overall wave field, and then you take the gradient of that, that gives you the force that's acting on the droplet, right? So you get an equation of motion, but it's not a nice ODE that we are used to. You have an integral differential equation of motion, right? But we can make progress. Now, in experiments, as you see in that video, you have two features of these waves. The waves have oscillations, and there is also spatial decay of the waves. So if we ignore the spatial decay of the waves and only say the waves have oscillation and consider a very simple form of the wave, so if we say this a of x is a cosine wave, right, just oscillations, and we put it in there, so if a is cosine, f would be sine here, and the equation would look like this, right? So I've considered a shape of the wave, which is sinusoidal, right? Now, it turns out you can transform this equation, this integral differential equation, into ordinary differential equation, and it gets mapped to a set of 3 ordinary differential equations. And if anyone recognizes this, this is the famous Lorentz equations, right? The Lorentz chaotic system. And the way the mapping works is, you can try this yourself. You just need to know how to differentiate under the integral sign using Leibniz rule, but you can do this transformation. So essentially, the capital X in the Lorentz system, it gets mapped to the velocity of the particle. The capital Y in the Lorentz system, that's this horrible looking integral force on the right side, and the capital Z is also related to that wave force, right? So we can do an exact one-to-one mapping between these sets of ODEs and this integral differential equation. And the sigma r and b in the Lorentz equation, they can be written in terms of this kappa and beta in the droplets equation, right? So this helps us, right? So we can forget about that integral differential equation and only worry about these ODEs. So if we understand what the dynamics of these ODEs, these Lorentz system, then we understand what the droplet is doing, right? Specifically the variable x, because if we know what x is doing, then we know what the velocity of the droplet is, and hence we can get the position of the droplet and its trajectory, okay? So let's try to see the behavior of these three equations. Now, this system of equation, it's a dissipative dynamical system here, right? And you can see it's nonlinear as well because you have these product terms, x times z and x times y. So I've just rewritten the same equations, but slightly rescaled. So it's a bit more intuitive for the droplet system. So I have two parameters here, r and tau. So think of r as the amplitude of the waves that the droplet generate, and then think of tau as the memory. So it's the time it takes for these waves to decay, right? So we have two parameters in the system, the amplitude of the wave, which is set by the size of the droplet, and the memory, which is essentially, in the experiment, the amplitude of your vibrations. All right, so if you are at very low memory, then the droplets don't move, right? As we were seeing before, the droplets bounce, but they will only start moving horizontally above a critical threshold. So below this threshold, the droplets bounce, but they don't move. So in this model, it will be a stationary point of the system, right? So how do we represent this? So if we look at here, we have three variables, x, y, and z. We know x is the velocity of the particle, so that has to be 0 because it's a stationary state. So if we look at this xz space, this would be a point at x equals 0 and some z value, right? And if we plot the position of the droplet as a function of time, it's constant, it doesn't change because it's a stationary droplet, right? So nothing interesting happens in the model if you are at very low memory, and this is also what you see in experiments. Now, as you increase the memory, at some point, you get a bifurcation in the model, a transition, and this stationary state becomes unstable, and you get a pair of new points in the system, and these correspond to constant values of x, one positive and one negative. So the positive value, you can think of your particle moving at a constant speed in one direction, and the negative value is moving at a constant speed in the other direction, right? So if you try to plot the motion, it's moving at a constant speed either to the right or to the left, right? So you get these two solutions. And again, this is something you see in experiments, right? You see these droplets moving at almost constant speed, right? And because we are restricting them to one dimension, they can only move either to the left or to the right. Now, what happens if we keep on increasing this memory parameter r? So it turns out that these simple-looking equations, these three equations, the complexity of behavior they give rise to is quite profound. There is a whole book written about these equations called the Lorentz equations. There is a whole book, and that only, again, touches the tip of the iceberg. So even though these look very simple ODEs, the complexity of behaviors that they can give rise to, it's quite a lot. So what you are seeing here is that after this steady state, you get a sequence of more complex and complex bifurcations. If you want to read, you can have a look at this book or just in general read about Lorentz equations. But eventually, after these complex set of bifurcations, you get chaos in the system, right? So some of you might have seen this famous Lorentz butterfly attractor, right? So in this phase space, if you plot the trajectories, it looks like a mess, essentially. And what the droplet is doing, if you plot its position versus time, the droplet is going between left and right, but it's doing it kind of more or less randomly. So on the Lorentz attractor, the butterfly attractor, if you are on one wing of the butterfly, you're moving in one direction. And when you're on the other wing of the butterfly, you're moving in the other direction, and your trajectory switches from one wing to the other wing in an unpredictable way. So your particle moves to the left or right in an unpredictable way. Now, this has not yet been seen in these experiments because it's very hard to reach this regime in experiments because of the accuracy of, you need to be very close to the instability without triggering it in the fluid. So it's not seen in experiments, but all of these models predict it. So I think it should be observable in experiments with enough refinement of the setup. All right, so let me end by showing you two different things. So first, let's see what happens to these droplets when you have more than one of them interacting with each other, right? So if you have two of these droplets, then they will sit next to each other, and the pair will move together at constant speed, right? So you have these doublets forming. You can get triplets as well. You can have three of them in a staggered configuration moving at a constant speed, and even quadruplets, right? So you can get collective translating motion of these droplets. Now, what happens? So this usually happens at low memory. They move at a constant speed. Now, as you increase the memory, if you have a pair of droplets, they will walk together, but they will oscillate sideways as they walk together, right? So you get what's called a promenading pair of droplets. Now, if they are not of the same size, if one is bigger and one is smaller, then the bigger droplet will drag the smaller droplet in its wake, and you have, again, a pair moving at a constant speed. Now, if you have a really huge droplet, it cannot survive on its own. It will just coalesce with the liquid. But if it's accompanied by another satellite droplet, then the smaller droplet will keep on orbiting the bigger droplet, and that's what keeps the bigger droplet alive. And we don't understand why this happens, right? So you have 2, 3. What if you have lots of them? If you have lots of them, you can get really nice crystal-like lattice forming at low memories. As you increase the memory, the crystal starts vibrating, jiggling, and then at even higher memories, it disintegrates, and you get a gas of droplets colliding with each other like billiard balls. Right? So you can see you get these interesting transitions in the collective behavior of droplets as you change the system parameters. All right, so I've been going on about these droplets and active particles, but one other reason why these droplets are interesting, and they have been interesting to study from a physics point of view, is that these droplets, they exhibit hydrodynamic analogs of quantum systems. So first of all, let me give you a disclaimer. This is not quantum mechanics. This is a classical system, but it's a classical system which is active, right? It's out of equilibrium. Now, people have done interesting experiments, and this is what they observe. So if you confine one of these droplets in experiments in a circular cavity, so it can only move within the cavity, then it will keep on doing this chaotic-looking motion. And if you keep track of the position of the droplet for a few hours, you don't see anything. But if you plot the probability distribution of its position within the cavity, then you get the plot on the right, right? So you get wave-like statistics emerging from the underlying chaotic motion of the droplet. And this looks very similar to what would happen if you confine an electron around a ring of atoms and either solve the Schrodinger equation or measure its probability density using an atomic force microscope. Right? So you get wave-like statistics in the system just from the underlying deterministic chaotic dynamics, right? You also get an analog of something like a tunneling behavior. So the boundary, the square boundary you see here is beneath the liquid. So it's barrier, which is submerged beneath the liquid. But the droplet usually gets reflected from the barrier because the depth of the liquid changes there. But occasionally, what can happen is the droplet can cross this barrier and go on the other side, right? So you get a kind of unpredictable crossing of this barrier, which is something analogous to tunneling. You can get even more things. You can do the double slit experiment with these droplets, right? So you can fire these droplets one by one at a double slit geometry, and see how they get deflected and at what angle do they end up going. And if you do that, people have done it, you don't get the same interference pattern that you get in quantum mechanics, but you still get wave-like distribution in the position of the droplet on the other side of the screen, right? So there is some interesting diffraction and interference going on, and it's not the same as quantum mechanics. You shouldn't expect it to be because it's a very different system, but it's still interesting that you get not just two patches, you still get a distribution which has peaks and troughs on the other side. And then lastly, people have done experiments by putting these droplets in magnetic field and have a harmonic potential. And when you do that, the droplets don't move chaotically anymore. They form these special orbits, and they only move along these special orbits, right? They are called limit cycles. So the motion of the droplet, in a sense, gets quantized if you look at the radius of these droplets and angular momentum of these droplets inside. Right, so you can get these very interesting hydrodynamic analogs using these active particles here. All right, so just to summarize, so we talked about active particles, right? So they are these non-equilibrium entities that consume energy and convert them into some sort of persistent motion. And when you have lots of them, you have active matter, and you can get all sorts of collective behaviors, right? Flocking, turbulence, and so on. And then we looked at two simple models of an active particle, right? We saw that it exhibits very complex dynamics, both regular as well as irregular, but we can use some of these ideas from nonlinear dynamical systems to kind of understand and rationalize these complex dynamics. All right, so I'll stop there. Thanks.
Thank you very much, Rahil, for your talk. We're now going to be taking questions for 30 minutes, so if you have a question, please raise your hand and I'll pass around the mic. Yeah.
For the first example you showed where we have tumbling and wandering motion,
Yes.
are those ergodic systems?
Right. So when it was chaotic?
Yeah.
Yes. Okay. Let's go there. Right. So let me see if I have the slide I'm looking for. So usually when it's doing the chaotic motion, it will explore phase space quite uniformly. But sometimes what can happen is you can get what are called sticky trajectories. So what will happen in these sticky trajectories is, so the droplet does chaotic motion for a while, but then every now and then it gets stuck into this periodic loop, as you see there. Right? So it's doing this periodic motion for a very long time, and then it will start again doing this chaotic motion and exploring other regions of the available phase space as well. Right? So because of this, you can get sticky trajectories where you spend a lot of time near a periodic looking orbit, but it's unstable, so you eventually leave there and explore other parts of the space, but because you can get stuck in here, you can spend a really long time.
Are there any more questions?
Thank you. In the example of superwalking droplets, the droplets get its energy when it's bouncing, so it's like discrete. In your model, it's continuous. How would you verify this?
Yeah, so what happens in the actual experiment, if you look at a high-speed video, is that the bath is vibrating, so it's oscillating up and down. The droplet impacts at some point, and the droplet only sees the waves at the point which it impacts. At other points, it doesn't care what the wave is doing beneath the droplet, right? So essentially, what the model does is, it only takes into account the wave when the droplet impacts, only that shape of the wave, right? So that's why you don't have the vertical bouncing motion in the model, and you can get away with it because you are averaging like the drag forces and everything, but the force on the droplet from the wave, you capture it when the droplet impacts the wave. And that's always the same because the droplet bounces in resonance with the vibration. So once you know what that phase of impact is, then you can look at what the wave looks like at that phase and then only consider the simple model where you don't have to look at the bouncing every time.
For the superwalkers, you assume in one dimension the disturbance caused by the droplet would be sinusoidal.
Yes.
But in 2 dimensions, you would expect to have a drop-off with respect to the radius from where the disturbance was caused. Okay. So would that affect the analysis?
Right. So yeah. So I presented a simple model here, but yeah, if you consider spatial decay either in 1 dimension or 2 dimension, the quantitative behavior changes in the parameter space, but the qualitative behavior still stays in the sense that even when you have spatial decay, if you go to high enough memories where the waves created by these droplets are decaying very slowly, you do still get a transition from steady behavior to more chaotic behavior. But it's just that that chaos would not be described simply by the Lorentz equations. It'll be an extension of that. But qualitatively, it still looks similar, as in if you plot the attractors, it looks like a double scroll attractor, but it might not be exactly the same equations.
Do we have any further questions? Thank you very much. Yes.
Thank you for the talk. Aside from the hydrodynamic quantum analog, are there any other applications for these superwalking droplets, or is it right now just an interesting system to study?
Yeah, so it's an interesting system. Apart from the hydrodynamic quantum analogs, it's an interesting system from this active matter perspective, because it's a very unique kind of active system, right? So as I was saying, this whole active matter field, it's only very recent, and people are still trying to understand some general principles that govern many of these active systems, right? So it's a unique active system because, first of all, there is inertia in these droplets, which you don't have in these microorganisms because you are at the very small scale, while these droplets are millimeter sized, so their inertia matters. The second is that there is memory in these systems because of these waves. And then it's an active particle that generates some localized environment, and then that environment drives these particles, right? So there are models out there, for example, that look at ants foraging. So ants, as they move, they leave some chemical trails which eventually fade away, and then other ants can interact with those trails, right? So here, they are not trails, but they are waves that these droplets are leaving behind, and then other droplets can interact with these waves, right? So it's a very, I would say, interesting system to study just from the active matter perspective itself, even if you don't look at the quantum analogs.
Hello. I'm just not pretty clear about, like, in what sense it's a quantum analog. Because you can't just have like normal standing wave, and you can say that it corresponds to quantum mechanics. So
right.
We're just looking at pictures of wave, and
no. So this is not quantum mechanics, right? It's an analog in the sense that you have a classical system, a droplet, where you can track its motion, right? But it performs this very complex motion, right? And then when you confine it in different settings, the statistics that come out from the underlying complex dynamics, it seems to be wave-like statistics. So it's only in that loose sense that it's an analog. So like you can't write down a Schrodinger equation for these droplets yet. People haven't, but right. So so that's why it's an analog or a similarity rather than in exact correspondence, right? So it's in this qualitative sense. That when you confine these droplets and look at their dynamics, their statistics in various situations, and compare it with a quantum system in that situation, sometimes you get similarities, but sometimes you also get differences.
sure, because I was just like how surprising this is. Like, is it very surprising? Because I'm just saying that in many contexts, I can imagine we have wave-like solutions that could look like quantum mechanics. Is this just one of those situations?
Yeah, so that's a good question. So I don't have an answer to like how general this is, right? So there's something called solitons as well, where you can have these wave-like solutions, but it's very peaked, and then that thing propagates, right? So there might be other systems where you get similar things as well. But I still think it's interesting and surprising because it's a classical system where a particle is coupled to its wave, and I wouldn't have expected naively for it to do all these things, right? To do these complicated motions. I would have expected a uniform probability distribution, so why does it do this wave-like probability distribution and so on? So it's still, I think it's an interesting system where it shows that a classical system as well, like some of these features that we talk about in the quantum realm, they might not be exclusive to the quantum realm. Like there might be analogous classical systems that do similar behaviors. So I think it's more interesting from that perspective that it's a classical system, but it does these surprising behaviors.
Okay, thank you.
Thank you for the talk. In one of the earlier slides, you were showing a system with a flock of birds.
Right.
How do you go about modeling that? Is that something you can predict or not?
Yeah, so physicists like to do simple models, right? So the entire bird is a point particle, right? And moves at a constant speed. So the very first model that people wrote down was by Vicek and co-authors. I think it's a paper from 1993, and the idea is essentially you have arrows, which are point particles. They like to move in certain direction, but it's not moving at, like the orientation is not constant. You add some noise, some fluctuations in the orientation, and essentially you apply a rule that each arrow or each bird, it has some horizon of its neighbors, and it tries to align itself in the average direction of its neighbors. So that's the simple model. And in that simple model, what you end up getting is that as you change the density of particles, if the density is low, then these things will just move around, jitter around independently as they move. But once you have some sufficient critical density, you get a phase transition in the system where it goes to a collective flocking state because it sees lots of neighbors and it tries to align in the average direction. So the entire system moves together in the same direction and you get a flock forming. Now that's a very, very simple model that was written down back in 1993. People have built on that to make it more realistic. So people now include vision cones and so on to make these interactions between particles more realistic. There is a single model out there that describes birds, for example, but there are many competing models that try to explain what's going on. So for example, something that has been not clear is whether each bird measures or looks at its neighbors based on distance, or is it just a topological thing that whoever is the nearest neighbor, no matter how far away it is, I will look at those and then I'll try to align, or is it not even that rule at all? It's something else that they decide on, right? So it's more like these are simple phenomenological model that gives rise to the same emergent behaviors, but it's not clear what is the actual interactions between birds that you would put into these models.